There are two kinds of error analysis or two kinds of errors on a physical experiment. The first one is the uncertainty due to instrumental precision. Not all errors are statistical in nature. That means that some measurements cannot be improved by repeating them many times. For example, assume you are supposed to measure the length of an object or the weight of an object. The accuracy will be given by the spacing of the tick marks on the measurement apparatus, the meter stick, for example. You can read off wherever the length of the object lines up to the tick mark or falls in between two tick marks, but you could not determine the value to a precision of 10 over 10 of a tick mark distance. Typically, the error of such a measurement is equal to 1/2 the smallest subdivision given on the measurement device. So, if you have a meter stick with tick marks every millimeter, you can measure a length with accuracy about 0.5 millimeters, while in a principle you could repeat the measurement numerous times. This would not improve the accuracy of your measurement thanks to the instrument you are using. This assumes that, of course, you have not been sloppy in your measurement, but made a careful attempt to line up one end of the object with the zero of the meter stick as accurately as you can, that you read off the other end of the meter stick with the same care. If you want to judge how careful you have been, it would be useful to ask someone to make same measurements in that order. You can both compare what you've got because there are different points of your perspective, and a comparison would improve a little that measurement. The other type of error is the systematic error. Systematic errors result when characteristics of the system we're examining or the instruments we use are different from what we assume them to be. For example, in a voltmeter we are using was calibrated incorrectly, reads 5% higher than it should. Then every voltage reading we record using this meter will have an error or 5%. Clearly, taking the average of many readings will not help us to reduce the size of the systematic error because it will always be the same. If we know the size and direction of the systematic error, that is not a real direction, from knowledge of the quantity of the instrument. For example, the meter manufacturer may guarantee that the calibration is correct to within 1%. Of course, you will pay more for a really small calibrated instrument than for a big one. So manufacturers always will change that kind of stuff. The other type of error is the propagation of errors. Even simple experiments usually call the measurement of more than one quantity. The experimenter inserts these measurements values into a formula to compute a desired result. For example, when you're measuring velocity that has components on their measurements, so there are multiple numbers, or when you're measuring speed or distance, or not distance, not acceleration, or other measurements and physical calculations that need more than one number. So we want to know the uncertainty of the result, okay, alright? And we list several common situations in which error propagation is simple, and that at the end we indicate the general procedure. If you're faced with a complex situation, as students have to ask to you, Mr. Wilhelm, of course. Many types of measurements, whether statistical or systematic in nature, are not distributed according to Gaussian examples, are the age distribution in a population, and many others. However, it can be shown that if a result R, let's name it, depends on many variables. The examination of R, aka result, will be distributed rather like Gaussian, and more so when R depends on more variables, even when the individual variables are not. The theorem in the following we assume in our measurement are distributed as simple Gaussians.